Skulle vi gå i gang?
Ja.
Klokken er 10. Godmorgen alle sammen.
God
Eller
formiddag.
god formiddag hedder det vel. Vi har nok været i gang i et stykke tid. Og velkommen til det her webinar, som vi holder med titlen klasse A++ Power Quality støjanalyse af elnettet. Og grunden til, at vi har valgt den titel, det er, at vi har Robert Schwarz med fra Østrig, der har noget teknologi, der faktisk kan måle den her power quality en del bedre, end det nogle af de her eksisterende standarder foreskriver. Jeg har også min kollega Kim Klante med, som også har en hel del erfaring inden for den danske elforsyning. Mit navn er Peter Harry Nielsen, og jeg er divisionschef i Wexøes Power Division. Vi regner med, at det her det tager 30-40 minutter, alt efter spørgelysten. Jeg kan se, at der stadigvæk er mange, der er på vej ind i mødet her. Hvis det er, at I har spørgsmål, så skriv endelig i chatten. Det er det, den er der til. Og vi kan også sagtens efterfølgende, når vi er færdige med præsentationen, tage nogle spørgsmål, hvis der måtte være noget, vi måske ikke lige har været rundt omkring. Men ellers så forsøger vi at komme hele vejen rundt med lidt omkring de standarder, der er. Nogle applikationseksempler, og så vil Robert Schwarz også gennemgå, hvordan vi kan måle de her ting. Så jeg tænker bare, at vi går i gang. Og jeg tænker egentlig, at Kim, jeg vil starte med at stille dig spørgsmålet. Hvad er power quality egentlig?
Jamen, det er jo, at man går ind og kigger på, vi har nogle problemer med spændingen, vi har nogle problemer med frekvensen og kurveformen, og så har vi også problemer med strømmene i nettet. Vi kan ikke alt det her, vi kan se alle de her forskellige målinger, der er taget ud for Sverige, rundt omkring i Europa, i Østen, de her udsving i frekvensen, som vi kan se. Og hvordan det her, det er jo ikke sundt for vores net, og det er ikke sundt for vores ting og sager, hvor vi selv tilslutter vores brugsgenstande, alt vores udstyr på i dag. Og hvordan opdager vi det, inden det går galt?
Okay. Ja.
Og hvilke symptomer ser vi, som power quality problemet er i? Og det er jo i mange tilfælde, at vi har jo mikroprocessorer i alt udstyr i dag. De svigter, og vi ser mange udfald rundt omkring i udstyr. Og hvad er det, der sker omkring os? Vi har aldrig set det før, og der sker mange fejl rundt omkring i dag. Vi ser, at automatisk reset af udstyr, vi ser også, at lyset dæmpes, når store drev startes op og ned. Vi ser udstyrsfejl, vi ser fejl i elektronik, vi ser strømforsyningsproblemer, vi ser softwarefejl, og vi ser også mange fejl ude i forsyningsselskaberne, som vi aldrig har set før. Blandt andet transformerfejl, muffefejl i jorden. Vi ser en masse fejl, som vi aldrig har set før. Hvad er det, der skyldes det her? Og det er som sagt nogle ting, vi går ind og kigger på nu her i de næste 30 minutter. Hvad kan det hjælpe os? Hvad er det, vi kan se og analysere ud fra?
Okay. Jamen, så kan jeg jo lige runde af, så der er ingen tvivl om, at dagens emne, det er jo faktisk yderst relevant, og som du også er inde på, så ser vi jo faktisk stigende problemer med den her dårlige spændingskvalitet i elnettet, og det er jo lige fra Energinet til artikler på nettet og ingeniørerne, der ligesom bekræfter det, og det er jo netop, som du selv siger, lige fra vores egen mobilopladere til store omformerstationer af elproduktionsenheder, der skaber problemerne. Og som du også var inde på, Kim, så er det jo noget med, at det kan eller vil resultere i fejl på de elektriske apparater, og det er jo helt sikkert, at levetiden den også vil blive forringet på udstyret, og det er jo noget, man måske ikke lige umiddelbart lægger mærke til, men det er også et faktum. Og så kan man så sige, nu er vi jo så heldige at have NEO Messtechnik med ombord, fordi det går lidt på, at mange af de målemetoder, vi har i dag, de er jo faktisk utilstrækkelige. Vi ser ikke helt, vi kan se, at der er et eller andet, men vi kan ikke rigtig se hvad.
Vi ser ikke det aktuelle billede på nettet.
Men jeg tænker, det er ved at være tid til, at vi stiller om til Robert Schwartz, som sidder i Østrig. Hej Robert. Good morning.
Hello, good morning.
And Robert, you should be able to share your screen, and I can see you have already done so. And NEO Messtechnik is still a young company, but with an extensive know-how within power quality, and we are so fortunate to have you as one of our trusted partners. So, Robert, before getting too much into power quality, maybe a few words about NEO Messtechnik, if people are not familiar with your company.
Thank you very much, Peter and Kim, for the introduction and also for the organization of the webinar. Thank you very much for this. Yes, also good morning from my side again. My name is Rupert Schwartz. I'm from NEO Messtechnik and I'm located in Austria, in our headquarters in between Vienna and Graz, I would say. So we have also a second office in Switzerland, and our manufacturing part is in South Korea. So we are in total, we are a small group, but we, as already told you, we have a lot of experience already in the power quality, the data acquisition market. We are coming from the companies DVTron, DVSoft, Genoa Wu, Norma Instruments. So we have really quite an experienced team with guys who are still excited to get some new technology on the market. So yeah, that's I would say the introduction about NEO Messtechnik. And then I will say we start directly with the presentation. Let's talk about classic power quality analysis. We have heard already some introduction, but if we talk about this, what do we actually mean? We talk about the voltage quality, where we see deep, slow changes, fast changes, voltage interruptions, of course. We have long interruption, flicker, swells, transients recording. We have harmonics. Here we talk about also then THD, and we see then the standard classical report EN5160 with all the parameters, like frequency, stability, and harmonics and harmonics evaluation, THD. But THD is actually a good topic to start with. Maybe if we think about the classic analysis, I will show you a short example at an electric vehicle charging station where we want to measure some harmonics. And if we think about THD, we have the total harmonic distortion. And if we compare this to the active power, actually, we see that the THD is rising when lowering the active power, actually. So we have at 0.5 kilowatts actually already a THD of approximately 50%. And this is because of the definition, of course, of the THD, which leads to the fundamental frequency, actually, and component. But therefore, the total demand distortion value is getting more and more common to analyze such of these effects, actually, of the distortion, actually. And this is the change here is that we are referencing to the actual load, the current load for this value. And here you see then also between the two, or between the higher and lower active power, we see that this is quite stable then. So THD is one hand. The one other stuff is then we talk about the unbalanced. So if you have a small system, for example, in our house, we have a photovoltaic and maybe an electric vehicle charger, one-phase electric vehicle charger. We see also unbalance in our grid. And if we compare this, or if we set this into comparison, we see the one phase, the red line, where we see there's a balance of load and generation, actually. And for the third phase, the green one, we see there's a higher voltage. So we see that we are actually producing power. And on the other side, we have on the second phase, the load process of the electric vehicle, actually, and we see therefore a voltage drop. So we have also quite an unbalanced system here then. And this could then also lead to affecting the limitations of the EN5160, but therefore it's also important to get some better or more than just only EN6150, 5160 analysis, and therefore we talk about the modern power quality analysis now more and more. And what does this actually mean is, first, if you think about the older technology, we had passive power electronics. So like TRIAC and stuff like this, we had in principle a sinusoidal waveform, but it was cut off, let's say for a dimmer, for example. And with the new technology, the silicon carbide technology we get with MOSFET and IGBTs, we see active power electronics more and more in our grid. And in the current waveform, you see this also, it is getting more sinusoidal, but you see that there's a lot of noise on this current actually. And this is because why we want to do this actually, we want to get more efficient here. That's the main reason why we change to this type of technologies. We want to get more efficient, we get more efficient, but we, on the other hand, we get high frequency components, high frequency supraharmonic emissions actually in our grid. And what are the effects actually of supraharmonics in our grid? This is quite different from we compare the grid and the electric equipment and the installations, for example. Regarding the grid, we have thermal stress. So it is really, if you think about higher frequencies or higher frequency current for capacitors, we see that this is then current consumption, the current is getting higher, and therefore compensation stations, like for example, they get under thermal stress and they will be also damaged, the lifetime will be reduced. There were also studies done about this, and we see this also in the grid, that this is getting also an effect, and this will have problems actually. Regarding disturbances, smart meter technology, we have here the power line communication actually. And the digital communication is also somewhere at this frequency spectrum up to 150 kilohertz. So we have also, if there is supraharmonic emissions in the grid, we have also problems with the digital communication. So we see that half of the smart meters, for example, were not able to reach because of disturbances in the grid, and therefore control is not possible, and also other stuff. Resonances, I think this is anyway a different topic. We can talk about this in, I think anyway, half an hour only about resonances and grid impedance changes. This is really something, affecting the grid as well with supraharmonics and charging stations, LCL filters, stuff like this. Losses of course, is also a problem. We have several % of losses due to harmonics. And for the electrical equipment and the installation, we see also thermal stress and therefore resulting reduction in service lifetime actually. We see also, because of this higher frequency component, we see also problems in changing the illuminance of the LED, for example. So we say that the LED is getting damaged in the long run, or even directly could also be, but more or less it starting to get less brightness, and therefore it will get damaged afterwards. Also here we see then resonances due to LCL filter components and stuff like this. So we have also oscillations or acoustic emissions here. So for example, during the charging process of an electric vehicle, you also can hear this. There were also done some research about this. Okay, and so if we see then supraharmonics and the standards actually, and we want to compare, if we talk about power quality, normally we see the region between 50, 60 hertz and 2 kilohertz. So up to the harmonics, up to the 50 harmonics, so 2.5 kilohertz. There's also the EN50 from the electrical kit, the standard. And what we see due to this nonlinear power generation and nonlinear loads in the grid actually, we see on the one hand side DC components, subharmonic, so the frequency spectrum also below 50 hertz and 60 hertz. But we see also, because of the more efficient technology, the IGBTs, the MOSFET technologies. We see also emissions in the higher frequency components up to 150 kilohertz or even more. And there we see now also the new, quite new standards, which really starts to regulate at least the voltage side up to 150 kilohertz. So with the IEC 61000-2-2, we see here the first regulation regarding the voltage for sure. And yeah, there's still a little bit of gap, but this will be built up in the future. There's also we will also talk regarding the standards in the future about the current waveform, the current limitation for harmonics. So this will be also one topic then in the future. And we are with NEO Messtechnik, we are covering broadband technology to really analyze supraharmonics and also subharmonics and all components from DC to 150 or 500 kilohertz. Okay, then let's switch back to our example from before, the electric vehicle charger. So we see on the one hand side, we have, of course, also a little bit harmonic loads, but we see also a lot of supraharmonics. And if we check this in the FFT, the current FFT actually, and we see the scope waveform of the voltage, we see, okay, a very nice sinusoidal waveform of the three phases. This is everything fine. For the current, we see this, also quite sinusoidal waveform, but we see these higher frequency components on the waveform actually, and therefore we see this in the FFT, for example, here marked in as switching frequency at approximately 20 kilohertz. So, but we see not only this 20 kilohertz switching frequency, we see also the multiple of the switching frequency up to 60 kilohertz in this case. So the spectrum here shows the current FFT up to 80 kilohertz, and we see here the multiple of the switching frequency also here. And if we talk about then probably at limitation for currents, actually, first we need to talk about the measurement method actually. So on the one side, we have the IEC 61000-430, which has the edition 3, which has defines the 2 kilohertz grouping. So you see here the 2 kilohertz grouping up to 150 kilohertz, but we have also the IEC 61000-47 with the 200 hertz bands actually. And first of all, the measurement method, it is mainly, here's the main difference. Of course, if you use 200 hertz bands, it consumes for sure a lot of more storage, and this is anyway one point, but there's also done a nice research about this, who is comparing this a little bit more in detail. But just to get a few examples out of this paper, actually, if we compare the 200 hertz band grouping and the 2 kilohertz band grouping, and first of all, you see at 40 and 60 kilohertz, for example, you are losing this information in the 2 kilohertz grouping. And if we talk about the value itself, for example, at 20 kilohertz, we see from the raw FFT, like the 5 hertz output of the FFT, like from 4.7 before the grouping starts, we see a value of 50 milliamp at 20 kilohertz. And if we do the 200 hertz grouping, we see 68 milliamps. And the 2 kilohertz gapless method, to mention, it's quite a little bit a little bit different to the original definition, because the original definition of the IEC 61000-430 edition 3 is just to use parts of the signal and then do the FFT actually. But here is the gapless method implemented in our system, which gets also more precise, but also we get here also a different value again. So we see a 75 milliamps, so between 50 and 75 milliamps, this is quite already a difference. You think about maybe, but this is a few milliamps, what can be the problematic here? Here also think about the effects of supraharmonics. They can be spread somewhere in the grid or quite locally. And here your LED light bulb, but what we have mentioned already before, the nominal current of a LED bulb is quite lower than this. And if you get this additional current, for example, which can actually happen, you see that this will also then really damage your electrical equipment actually. Okay, then let's talk about the photovoltaic. So here you see also regarding the voltage and the current actually. We see here the fundamental part, and here that's approximately 17, 18 kilohertz. We see the switching frequency in the current waveform of the FFT. And we see also multiple of the current waveform. And in the voltage, on the voltage side, you don't see an effect at 18 kilohertz approximately, but you see an effect at 40 kilohertz. So you have also some parts, and this can happen probably to the grid impedance actually. So here is already, or here could be already a problem, a resonance, and maybe this is then also something we can talk about then in the maybe following up webinar when we talk maybe about grid impedance measurements and grid impedance changes. And this is then also an effect. So you see also it could be this also on the voltage side, but it must not be on the voltage side visible. So it is quite important, and the measurement system needs to be possible to measure also these high frequency components you see. And if we talk about photovoltaic, we talk about photovoltaic inverters, and we also talk normally about transformer-less photovoltaic inverters. And here was also here this is also a part of an research done of a paper where they compare 3 different types. They don't say which types actually, but therefore they call it type A, B, and C. But they are quite common in Europe or worldwide actually. And what we see here actually in the FFT is that they are different types of it. It don't really depend on the power itself or the current, but they inject actually a DC current to the grid actually. And you know, a DC current, this is not so good for again our electrical equipment in the field. So for example, our transformer station, they will go into saturation, and this could be also problematic. They get lifetime reduction, they get heated up, they have really problems with this, and at the end get also damaged. And the second effect, which is maybe in northern Germany also starting to get more and more important, or in the northern countries, it's already known about this, because in Finland there were already some measurements done long time ago. We see also some geomagnetically induced currents in the grid actually. So during a geomagnetic storm, for example, we see that we get a geomagnetically induced current in our grid, and therefore we also get DC currents at our transformer stations, and we put them into saturation, and it's actually we'll get lifetime reduction. We have the same issue of thermal stress, and then at the end it will get damaged, and we have problems in our grid. And if we look at the picture on the right side, actually we see that it is quite a long time ago, so we are aware about this quite a long time, I would say. We see it in 1991 actually. We see that this is already quite a huge change actually in the grid, in the current, right? So this is also something we need to be aware. So we have also DC parts in our grid, and we have measured, for example, the voltage at the transformer station over 2 days. Here you see the higher frequency component. So we are approximately here at 80 kilohertz. So this is at the photovoltaic part measured. So we see over the day, let's say we see some power generation. Therefore, the emission you see the emission actually at the transformer station measured, the higher frequency component. In the night, of course, there's no emission, but then the second day again, we see this also here. And for the current, we have done more or less the same measurement. And here at 1 day, we see also at 80 kilohertz current, higher frequency current at the transformer station. And this is, so the effect is already there, I would say, and therefore we need to be aware, and we need measurement equipment who is doing this analysis, or possible to measure this on the first hand side, and then also to give the chance. Otherwise, you are also looking in the dark and you will find nothing. And for our mobile power quality analyzers, we have actually two solutions set up in the last years. And the one is our called PQA 7000. It's class A. We have 40 kilosample per second, so it's for the lower requirement, I would say. We have 4 times voltage inputs, 5 times current input, the accuracy with 0.05%, and we have safety category 3 and 4 with 600 and 1000 volt. And we have all the extended PQ functionalities because we have the same software, we have the same report analysis. The only thing is the bandwidth limitation, but therefore it's also cheaper, right? And we have the PQI 8000 up to with the possibility of up to 1 mega sample. We have different configurations with 4, 6, or 8 current inputs. We have then additional analog inputs. I will show you this later. 0.05% accuracy here also. Safety category the same. Also here the extended PQ functionalities. So if we talk about the future power quality analyzers, we see Supraharmonics even up to 500 kilohertz for voltage and current actually. And we have high accuracy, 500 kilohertz bandwidth. We see also switching operation, high frequency events in the current waveform. So we have also envelope trigger. So envelope trigger to cover these events, therefore also doing the FFT actually. And also vector scope can be shown in the analysis during this event. And then we have systems dynamics, grid codes, rate of change of frequency, phase angle jumps, grid impedance getting more and more important, I would say, and also symmetric components, disturbances. This is quite known, I would say. So regarding the instrument, so we have multiple inputs. So we see here from the voltage side, we see a channel to channel and channel to ground isolation. So we are also possible to measure DC and AC or mixed signals actually, or common mode signals, because we have a quite high signal to noise ratio. Then we have for the current inputs, we have these inputs, these multiple inputs, where we have the possibility to have the integrator inside. So with the, if you think about the Rogowski coil measurements, this gives us a huge advantage, because we can measure with the same coil actually 1 amp or 30,000 amp. So this is possible in the same way here. And we have also power supply. So we have unipolar and bipolar power supply for AC/DC current clamps, or for flux gate transducers can also used. And we have additional inputs like for analog inputs, wind, solar input, digital inputs, counter, or RS-232 or 485 inputs. Synchronization can be done via GPS. We have also the possibility for the easy remote connection via UMTS or via standard LAN or Wi-Fi connection. So this is also possible. Fast viewer, team viewer, this is everything installed. And multiple touch display, sunlight readable. We have the battery pack, and the charger is integrated, so you directly go with your cable to this instrument or device, and therefore you don't have this external charger. Regarding the current measurement, we have also the possibility, beside of the direct powered instrument by the instrument and the multiple measurement ranges from 2 millivolt to 10 volt, we have also the possibility to do a sensor correction. So through the whole frequency band, we can do an amplitude and phase correction for each sensor. Actually, we're doing this per standard for our Rogowski coils. And if it's needed, also for the really high bandwidth side, and therefore we achieve a really high accuracy also in the high bandwidth. Okay, and we have for the instrument versions, we have 4 current input, 6 current input with analog in or digital in, or 8 current inputs actually. So these are the types of these. For measurements in higher voltage levels or all voltage levels, we are also prepared. So voltages up to 1600 volt can be directly measured up to 500 kilohertz. So this is quite important. So we have the full bandwidth on our voltage inputs. Then we have the current measurement via Rogowski coils, for example, also up to 500 kilohertz. If we are in the medium voltage range, we use voltage dividers. We have here some partners in behind where we know that our our instrument is working perfectly with the voltage divider, also regarding the bandwidth. And sometimes they have also then, for example, 3 volt square root of 3 output secondary side. We have also the voltage input on our voltage side to measure these small voltages also with the high bandwidth. And regarding current measurements, we're using here Rogowski coils because we're also talking here regarding measurements on cables actually. And for the highest higher voltage level, up to 380 kilovolts, we have also two manufacturer in the back where we know that our instrument is working perfectly and also up to high frequencies. If we talk about voltage transducers and medium voltage, and we look at the research done from the secret guidelines, actually, we see that the standard voltage transducers are not usable, or only for 10 kilowatts actually, are usable for the analysis up to the 50th harmonics. So what you actually need is then, for example, RC divider or optimized RC divider, what we actually using for higher frequency analysis. So you need to be also in contact with the manufacturer if you look about this and if you are compare this actually, so that you know that they are fulfilling the requirements to get these high frequency components also measured. And for the highest voltage level, we have then for sure, it's a setup like voltage and current transducers actually, and just to show that this is also possible, and you know that this is not done in a few days. So this really needs to be planned from the grid operator or set up during a new transformer station setup or stuff like this. So this needs to be anyway done in the longer run. But up to 50 kilohertz, we have done some measurements already, and with the sensors, for example, we see also DC currents in the highest voltage levels actually. And regarding comparison of for high frequency, it's not only important to have this this signal to noise ratio. This is quite important because otherwise your signal will be lost in the noise actually, and you're not aware that there's actually a problem. And with our technology, we see that we have these small signals can be accurately detected, and this is important that we see this actually and that we know that there's a problem, and this is the benefit against the standard PQ analyzer for us and for our instruments because our excellent signal to noise ratio. Regarding the software highlights, I think our instrument covers the standard requirements anyway, but we have also a lot of additional extended power quality analysis tools, and which will give you more better and more flexible and intuitive way to analyze your data actually. We have a standard schematic, clear structure schematic, we have vectorscope, we have the pure waveforms, oscilloscope, the higher frequency components, table view, and in the analyze mode, we get all of these functions for disturbances, transients, and alarms can be added. And of course, the most important thing, of course, you get one click report according to, I would say, any standard, because you can also define your own PDF document. So it's quite easily to create your own report actually, which is for you important. But you can also get the standard report like EN 5160, IEC 61000-2-2 or -2-4 actually with the 3 classes. So what you're looking at. There are also the possibility to add in the local distributions, like in Austria, for example, the DACH standard for the current limitation actually. And you can also do export and use other programs because it's Windows based. So we see a lot of features actually here and a lot of power quality parameters up to high frequency. So we have the disturbances at the system dynamics and therefore class A++ instrument prepared for you and for your analysis. And maybe some topic for the future, because I want to just add a few words about this. We have also developed a small grid impedance analyzer box or excitation unit actually, and we are able to control and operate this with our power quality analyzer. So you get an additional box, quite small. You have also category 4 and the UL case actually, and we can do in a very short time also a grid impedance analysis up to 150 kilohertz or 450 kilohertz, because we have two different versions price-wise and also from the measurement itself. We're using the 4-wired measurement, and we can do therefore grid impedance analyze between two phases or between a phase and the neutral. And yeah, this is really something in addition and gives us also a big advantage, I would say. But regarding grid impedance analysis, we can talk about a half an hour again, I would say. And yeah, regarding grid impedance, just a few words. We see in the grid more and more high switching frequency AC-DC conversion or DC-DC conversion, and mostly we have passive LCL filters. For example, photovoltaic inverters, they have more or less always passive LCL filters connected to the grid, which leads to resonances in your grid impedance, and this is then really problematic and could lead to also additional damages in our electrical grid, I would say. Yes, I think this will brings me more or less to the end, to my last slide. Regarding the energy source and the different power generation technology, inverter, asynchronous or synchronous generators, we have the power quality parameters like harmonics, unbalanced flicker, voltage changes or voltage height, frequency behavior. But we have also, what we've talked about now, new parameters like DC parts getting more and more important. We see this at photovoltaic parks, for example, subharmonics, supraharmonics up to 9 kilohertz or to 150 or even 500 kilohertz. We see resonances in the grid and therefore grid impedance actually. Measurement will get more and more important. And with our combination of the two instruments, I think we are well prepared for the future and also for the future technology or the changes in the standards actually and the regulations, and also with the measurement method what we have talked about, we are really prepared for the future power quality analysis. So thank you very much for your attention. Thank you very much. I think I'm precisely at 30 minutes approximately. So
perfect, Robert. Yeah. No, thank you very much, Rupert. For sure, there's a lot of things going on within the topic of power quality, and we can also see that from just your latest developments. And also thank you very much for a good presentation where we can also see that there's a lot of things to cover in this specific topic. In Danish, I er meget velkomne til at stille spørgsmål. Det kan godt være, at jeg har muted et par stykker af jer, så hvis der er spørgsmål, skriv den inde i chatten, eller spørg bare direkte, åbne jeres mikrofoner, så kan enten Robert eller også min kollega Kim helt sikkert svare på det, eller finde ud af, hvordan vi finder det rigtige svar. Så er der spørgsmål? Questions? Eller er det et meget stille audience, vi har? Det tror jeg. I'm thinking, Robert, I have a question. I'm thinking very much the applications and the interest that you see in this. Is it very often because your customers are having problems in the grid that they want to analyze and figure out what is the reason behind, or is it just as much maybe documenting, you could say, installed components into the grid, making sure that when you finalize your project and you're connecting it to the grid, then you at least have a documentation that you are fulfilling all the specifications. Yeah, a comment
Yes,
on that.
there are actually two sides still outside, I would say, because one, they are only interested in EN 5160, and they will at the moment not be really aware of all the other things happening in the grid. And we see also really a lot of also grid operators who seeing that there's going on something, and therefore they see that the common power quality analysis is not enough anymore to analyze this, and they are already jumping up on, for example, our system to really be on the one hand side, okay, EN 5160, this is more or less anyway not really a problem, but also from limitations, if we talk about 61,000-2-2, for example, this is maybe also still okay, but then you sometimes have also local requirements also for a current waveform actually, and then it is good to have all of this information already covered to be also prepared then if the standard will be really a standard actually, then an international standard, and we are on the way to that, I would say, to be also prepared. Because, for example, if you have at the moment also current measurements limitation from the bandwidth side, you're never able to see anyway a higher current flow at the higher frequency components, which will, of course, then damage your electrical equipment again.
Yeah. No, but as we started saying in the introduction, we are seeing an increased interest, and it is, of course, Denmark is also having a heavy investments in this green transition. So we are seeing problems on this on the grid for sure. All right. Any other things? No. And some of you have asked, nogen af jer har spurgt, hvordan med Roberts præsentation, og nu når det her det er færdigt, så laver vi en optagelse, og vi laver også en kopi af hans slides, så I har dem til senere. Og så kunne det godt være, at vi gav jer et kald for lige at følge op, om der er noget, vi kan hjælpe jer med. Så skal vi lige give sidste... I think, Rupert, the audience is very quiet, but they have asked for a copy of your slides. So
Yes.
I think it's interesting enough anyway. If there are no further questions, ikke flere spørgsmål, så tænker jeg bare, at vi slutter her. And also to keep time, 45 minutes. So thank you all. And og tag endelig kontakt til os, hvis I har brug for yderligere inden for power quality. Thank you, Robert. Thank you from Austria.
Thank you very much, and greetings to Denmark, and see you next time.
You too. See you.
See you.
Bye bye.
Ha en fortsat god dag.